In this video, we're going to cover section 7.5, Strategy for Integration, and a part of 7.6. Neither of them are very important, I have to say, so please sit back and just listen to what I'm talking about and spend your time doing exercises. Section 7.5, Strategy for Integration. This is not a usual section. This is a summary section. We do not deal with any new technique here. It just summarizes everything that we have been through here. It does try to give you some step-by-step process, but please be warned, that step-by-step process doesn't always work. First, it begins with a summary, a grand summary of entire Calculus 1 through this table of integration formulae, and there are 20 of them, and all these we went through in Calculus 1. And of course, if you want to find out, whether they are true, start from the right hand side and then take the derivative and see if you get the integrand back. And that's going to be useful in a very first step. If you have rather complicated integral, then try to simplify the integrand, and you have to have certain directions you have to take. What kind of direction am I talking about? We are headed some standard functions that show up in this table, like power functions, as we saw over here, power function plus another power function, or trigonometric function, as we have done in this manipulation, or another trigonometric function. After manipulation, we have 2 sine of x cosine of x, which is sine of 2x, so another trigonometric function. So that's the easiest case. However, everybody's passed calculus once, so I don't think any of these problems will cause any kind of trouble to you. So the kind of problem you'll have to expect in this class will be a little bit more complicated ones, and step 2 deals with those kind of things, or step 2 is the starting point of those kind of things. Look for an obvious substitution. If you have an obvious substitution, as in this integral, just take it. And if it is not so obvious, in that case, you'll have to go to step 3. Classify the integrand according to its form. Do we have trigonometric functions, sine, cosine, tangent, secant, or cotangent, cosecant, things like those? In that case, we'll have to use the techniques we went through in section 7.2. What if we have a rational function? We'll have to use techniques in 7.4, get a quotient and then the remainder over the denominator, and then factor the denominator, and then solve the equation, the system of linear equations, and then find out the coefficients and so on, called the decomposition by partial fraction. It's a long process, but in some cases you'll have to do. Most of the time I'm going to stick to the simpler case where the denominator is quadratic, but who knows. Integration by parts. Well, there are some obvious integration by parts, there are some not so obvious integration by parts, but either way you should be prepared. Let me show you some obvious cases. Just a moment, let's pause it. Okay, integration by parts. There are some obvious integration by parts. Here is the integration by part formulae, and the form that I prefer, or the differential form that our textbook author prefers. And which is which? Which is u and which is v prime? Here is the hierarchy table that can be very useful. Logarithmic function and arctangent function has the strongest tendency to become u. Integer power function comes next. Sine and cosine comes next, and exponential function has the strongest tendency to become v prime. So if you have any product of two functions that comes from this hierarchy table, then you know that's going to be an integration by part problem. In some cases, we'll have to deal with radicals, and radicals are always tough to deal with. And if you have linear function in this radical like d2 here, then it's no big deal. all you have to do is to change it into power function ax plus b to the 1 over nth power, and all you have to do is to deal with the reverse chain rule, the division by a, we went through in calculus 1. What if we have quadratic inside, especially quadratic irreducible? In this case, we'll have to make it into some complete square and then try some trigonometric substitution. We went through that in section 7.3. Again, those are rather cumbersome, so I must admit there is relatively low probability that I'm going to write those kind of problems. I may write just one exceptional problem, but not more than that most of the time. And finally, step 4, try again. And you may think it is outrageous to put try again as a legitimate step-by-step process, but that is typically the case for complicated integrals. Try something and it doesn't work out. Try something else, it still fails. Try something else again. And that's the standard process for integral computation. What can you say? That's the nature. So please be prepared to do something over and over again. Well, that's about it. So let's do several application problems, or some exercises. First example, that's one of the easiest one, tangent cube over cosine to the cubic power, and all you have to do is to recognize cosine, 1 over cosine is secant, so you can rewrite 1 over cosine into secant, and this is what you get, tangent to the 3rd power times secant to the 3rd power. And what did he do in section 7.2? The tangent has odd power, so y substitution, y equal to secant of x, will do the job. If you don't see that, or if you don't like that, there's an alternative method using sine and cosine, which is given here in this textbook. Personally, I don't like it, so you don't really have to bother. How about the next example, e to the square root of x? And this is a typical example that you have obvious substitution. It's really obvious that you'll have to take u substitution, or personally I prefer y substitution, y as square root of x inside of a composite function. If you do that, and you're going to get integral like this. And the final integral in the right hand side, is it better than before? At this moment, I've seen some students who are just giving up or trying to find something else and are failing. Actually, this is okay, because this one in the right hand side is an obvious integration by part problem. Remember the hierarchy table? Power function times exponential function is a product of two functions. Both of them came from the hierarchy table, so this is integration by part. So you can go through that from here, and then you're going to get an answer. Example 2 is a standard problem, not outrageous one. Example 1, of course, was one of those easier problems. How about the next page? Example 3, this is actually an easy problem, but tedious. It's a rational function. The numerator has higher power, so what you have to do, you have to divide the numerator by denominator by long division, and then get quotient plus remainder over the denominator, and then factor the denominator, and then set up an equation a over first factor plus b over second factor plus c over third factor. Manipulate the numerator, take the common denominator, manipulate the numerator, and then compare the coefficients. Set up the system of linear equations, find out a, b, and c values, put those all into the partial fractions, and then take the antiderivatives and get 3 logarithmic functions. Oh my goodness, if you actually sit down and do that, it's going to take a long time. Everything is easy and simple, but it's just long and tedious. Personally, I don't like this kind of problem. I haven't written those kind of problems in the exam for ever, to tell the truth, ever since I began teaching in college since 1994. But who knows, I may end up writing one. If the denominator is quadratic, then you should be able to do this by, shortcut formula. Example 4 is rather simple because there's an obvious substitution, u as the inside of the square root. No big deal there. How about example 5? That's gonna be a real challenge. Did I say radicals are always cumbersome? Well, here's one such example. Substitution is not gonna do very well, but substitution, the textbook author says substitution works, but I don't know, it'll probably end up with some really complicated rational function, and you'll have to do this decomposition by partial fraction. So the textbook author suggested some ingenious technique like this. Multiply 1 square root of 1 minus x, the conjugate of the denominator, to both numerator and denominator, and numerator becomes the square root of 1 over x squared, so we just lose the square root. Denominator becomes square root of 1 minus x squared, and what do we have? Square root of 1 minus x squared. That looks like a trig substitution. Indeed, we decompose that integral into two. The first integral here is trig substitution. X is sine of theta, or this will turn out to be arc sine. The right hand side will be a u substitution, u equals 1 over x squared, and then finish the computation. We have this kind of function, arc sine plus square root of 1 minus x squared. The first integral is coming from trig substitution. The second is coming from substitution by u equals 1 minus x squared. Weird, but these kind of problems do exist. Well, what if your integral is even worse than these? In that case, you'll have to use either computer algebra system, which we will talk about in the next segment of the video, or you can use integration table. Integral table, well, I want to save some time, so I just went to a search engine and typed in integral table, and then there are hundreds of them, and then I just click the first one. Anything is pretty much the same. They're all the same, actually. Very standard, but I just wanted to show you what an extensive list we have. So basic forms, and then these, and then a little bit more complicated integrals, and then even more complicated integrals, still going, and there are hundreds of them. And what you need to do is get your problem and then see what kind of problem this is, and compare that with some of those formulae here in this kind of integral formulae, integral table, and then find out your answer. 2 pi x arctangent. Oh, actually, this is not too bad at all. This is integration by part. Why is this problem here? Something like this. Okay, you can find out that something that involving a squared minus u squared in the integral table. Let's go over to integral table, and it must be relatively on top. Is it? Yeah, they're something like this, a squared minus x squared, or 1 over a squared minus x squared, something like this. So either formula number 30 or number 33 or 34, compare those kind of things with your problem, and then get your answer, and it'll turn out to be an arc sine. Integral table to evaluate x cubed sine of x. You can use integration by part 3 times to get this one done, but that's too cumbersome. So you can do it through integral table, and then some trig function and some power. There must be some reduction formula related to that in the integral table. And, well, I lost patience. You can find out. And the rest is left to the students.